do want to remind you of some of the symbols of different number types, and some of these you may not have actually seen before, but many of these will probably look familiar. When you're looking at, think of the big set of numbers is what we call the complex numbers. Now, complex numbers can take on many different forms. We can see those that are purely real numbers, like 2 would be an example of a complex number. Also, the number, let's say negative 3i, that's also a complex number. But then complex numbers can also be combinations of these types of numbers. So, for example, the number 4 plus 3i, all right, that would be a complex number. So complex numbers are really just any kind of number that you can possibly think about. So that's the big set. But then you've got subsets that fall within the complex numbers. And then this first group that you'll see right here, these all kind of nest very easily or very nicely inside of one another. And so in this particular case, if you're looking at the set that's on the outside of this particular grouping, we have what we call the real numbers. Now, the real numbers are just like any number that you would see on the number line. And basically, it's any kind of number that doesn't have the I in it. So if you think about the complex numbers, take off the ones that have the I's in it. What you have is you have the set of real numbers. And then inside of that, you'll notice that you've got 3 other sets that are nested inside of the real numbers. We've got the rational numbers, we've got the integers, and we've got natural numbers. Now, the set of rational numbers are going to be those that we can write as a fraction. And it may not be that it's necessarily listed as a fraction as it appears in the beginning, but you can write a number as m over n, where m and n are integers. And so we'll have to talk about what integers are in just a minute, but the way we would write this is we would say it's a number of the form m over n, and m is going to be an integer. Now, to kind of cover some symbols here, we say that m is an element of. All right, so this little symbol right here just means element. And then we also have to have n as an integer. So n is an element of the set of integers. All right, and this z here is the same thing as this z right here. All right, so it means it's an integer. So we'll talk about what integers are, but right now it's a number of the form m over n, where m and n are both integers. And of course, since n's in the denominator, n cannot equal 0. So that would be your set of rational numbers. Now, any number that's not rational is what we call irrational. And there's not really a nice place to put that inside of this subset. So just know the reals are either rational or irrational. So now that we've used the symbol for integers, all right, what in the world is an integer? All right, an integer is just going to be positive and negative numbers, but without anything except for perhaps you could think of it like a 0 past the decimal. So if we had, I'm going to say this set of numbers, -2, -1, 0, 1, 2, and so on. All right, and so it goes in both directions, so it can be negative or positive, but it's just the actual numbers themselves without, like a 1.5 is not an integer. And then you've got what they've nestled inside of here as what they call a set of natural numbers. Now, when I always see natural numbers to me means that what you naturally start counting with. So it would be like 1, 2, 3, and so on. Now, some people use that and whole numbers interchangeably. I've never done that before, but I have seen some textbooks do that. When I think of whole numbers would start with the number 0 and then keep going 1, 2, 3, and so on. So, really, if you wanted to, you could even put another subset inside of this that would surround, it would be inside the integers, outside of the natural numbers, which are the whole numbers. So that starts with 0. All right, so that's some of the numbers that you have there. And then, of course, the imaginary set that we mentioned earlier as being part of the complex numbers, we also see that down here. And so that's just saying that anytime you have an imaginary number, it's not going to be a real number, a rational, an integer, or a natural, because you see this definite space in between here. All right, so there's no intersection between those two. So the set of imaginary numbers would be just those that have the I in it. So like this negative 3i that we saw over here just a few minutes ago, that would be a number that would fall into this set right here. All right, but the 4 plus 3i, that's a mixture of real and imaginary. So that would be in this set that you kind of see in this gray that's not inside of any of these other circles. If you're not familiar with all the different kinds of sets of numbers, if you'll click on this link down here, it'll take you to a place where you can actually see more about the different kinds of sets. Hopefully this is a review for you, but if you haven't seen some of these or haven't seen the symbols used, please look at that link. Now what you'll see in these, you see these like bold types, so like the R is like a bold R for real numbers. Now a lot of times when we're writing that freehand, we obviously, it's kind of hard to write it as a bold. So a lot of times what people will do is they'll put a double line on the R, so that just means the set of real numbers. For rationals, I've seen people do, like a Q with a line through it. So there's variations of these things that you can do. Other things you can do would be to maybe restrict the set a little bit. And so like, for example, let's say that you wanted to talk about the set of positive integers. Well, one thing you might think is, we could just call that the natural numbers, because that's actually exactly what it is. But sometimes you'll see people do things like this. They would say it's equal to the integers, and they'll put like a little plus as a superscript. So it's just a way to restrict whatever the set is that you're talking about. If you wanted to talk about maybe a set of non-negative integers or non-negative any of these symbols, the only thing that I've ever seen here is people will write the symbol for integers and then they'll just write NONNEG. And so that actually restricts it to just being the non-negative integers. Again, there's more than one way to write these things, using maybe combinations or other symbols as well, but these are very common. Now, one definition that we're going to be using in connection with a property is the closure property, and we say that a set D is closed under an operation. We're just using the symbol star, but that star could be addition, subtraction, multiplication, so this symbol right here is just representative of a lot of different symbols that you could have. And that's going to be true if for X, that's an element of some domain, and Y is an element of some domain, that if you do that operation to those things, that you also get another element that's in that set. All right, now the D's here just represent, could be real numbers, could be integers, could be rational numbers, so it's just representative of some sort of domain that you might have. All right, so let's look at these examples down here. We're asked whether these are true or false. We don't have to prove them yet, but just, are they true or false? So what we want to know, first of all, is the set of integers. All right, and remember, integers would just be the positive and negative numbers like this. Is the set of integers closed under addition? Well, that says if you take any two numbers from this set and you add them, does it also give you another integer? All right, and the answer is certainly yes. You can pick any two that you want to. If you add those, you're not going to get, something, you're not going to get like 3.5 when you add two integers together. All right, every time you add two integers, you get another integer. And so this one here would be true. All right, but the next one says the set of irrational numbers is closed under division. Now, we didn't really talk about what irrational numbers were, but I know you've probably heard of these. Probably the most common one that you would give as an example of an irrational number would be the number pi. All right, so let's just say we look at the number pi. All right, well, to be closed under division, that means that if I take any two irrational numbers and I divide them, then I'm also going to get another irrational number. All right, so that would say that, if I took pi and divided it by itself, I should get another irrational number. But if I take pi divided by pi, I get 1. And 1 is an integer. 1 is not an irrational number. Now you might say, well, why is it not an irrational number? Maybe that's, maybe the set of integers is a subset of the irrationals. All right, well, it's not, because if you think about like pi, it's 3.14159, etc. The decimal value there never ends and it never begins a repeating pattern of any sort. So an irrational number would just be basically a real number that's not rational. You can't write it as a fraction, and it always keeps going when you write it in its decimal format, but it never begins a repeating pattern. All right, so this one would be false. The next one says the set of integers is closed under subtraction. And I think you can probably see that for the very same reason that addition worked, subtraction works as well. All right, and the set of natural numbers is closed under division. All right, and a natural number starts with 1 and keeps going 1, 2, 3, 4, and so on. So what that would say is that if I take any two natural numbers and I divide them, then I should get another natural number. So if you can think of any case where that doesn't happen, then it would be false. I think I can come up with an example real quick. If I take 1, which is a natural number, and divide it by 2, which is also a natural number, I get 1/2. All right, but the number 1/2 is definitely not a natural number. And so actually it's a rational number, but it's not a natural number. And so the answer here would be that it's false. Now we're going to be needing this because we want to be able to say when the closure property, which just means that something satisfies this definition, the closure property is going to work for integers in many cases. So if I add two integers, I get another integer. If I subtract two integers, I get another integer. And so many times we will want to not have to write this out every single time. So we would say, oh, well, the set of integers is closed under, and then we can say, okay, well, we know that it works for addition. If I add two integers, I get an integer. We know that it works for subtraction. Now, we just said that, I guess the set of integers is closed under addition. We said that here. We said under subtraction here. Does not work for division, all right, because if you take two integers, it's possible to divide them and not get another integer. But what about multiplication? Yeah, that works too. If you multiply two integers, then you are definitely going to get another integer. So a lot of times people will say, oh, this is the closure property. And we can use that to shortcut some things in the future. So the closure property of integers, it's closed under addition, subtraction, and multiplication. A couple of other definitions that shouldn't be anything new to you, but maybe the notation that we're using might be. All right, the first one says that an integer n is even. We know what an even number is. All right, it's even if and only if. All right, so first let's talk about what this if and only if means. If and only if means that it just goes both ways. So if it's even, then this thing after this green circle, or the shape that I just drew, is going to be true. But it also means that if what appears over here is true, then that's going to go the other way as well. All right, so if and only if just means, if the first part's true, the second part is, and if the second part is, the first part is. So that's, and all definitions are that way. All right, so that's if and only if. All right, the next thing that we see here is this backwards E. All right, now if you haven't seen this before, this just means there exist. All right, so what we're saying is that an integer n is even if and only if there exists a k that's an element of the integers. So that just means there's some integer out there such that n can be written as 2 times that integer. All right, now it looks like we've taken something really simple to understand and made it really complicated. This is going to be very important in the next section for us to have a way to write these things. So a real simple example here would be, like the number, I don't know, maybe 6. All right, so if I take the number 6, I can write it as 2 times 3. All right, and so the 3 here would be the k that I'm looking at. This 2 comes from this 2, and the n is the number in question. So 6 is even because it can be written as 2 times something, and then that something that we have here has to be an integer. All right, and then we say a number is odd if and only if there exists a k such that it can be written as n equals 2 times k plus 1. And so, if we looked at the number 7, maybe, that would be 2 times 3 plus 1. And in this particular case, this number right here is still the same thing as the k was before. All right, it's still an integer, and so 7 would be an odd number. Now, our examples that we're going to have are not going to be this simple, but the same idea will apply here.